Hello, I'll be presenting a joint work done at Carnegie Mellon University with Vijay Ramamurthy, Ruben Martins, and Umut Acar. I'll be talking about program equivalence for assisted grading of functional programs. In just about any computer science course, writing programs is an essential component of the learning process, and grading and giving feedback for those programs is a primary component of the teaching process. But as more and more students decide to study computer science, it is becoming increasingly difficult for universities to meet demand. Consider the simple implementation of quicksort on screen. It might just take only a minute for a professor or TA to examine this and verify that it's correct, but if a course has 300 to 400 students, and each student is submitting an assignment containing several programs like this, then it can require far too many man-hours to grade every submission by hand. The most common answer to this problem is to turn to autograding. Rather than grade every submission by hand, we can automate the process, testing each submission against hundreds of input-output pairings, and assign a grade based off of how many tests are passed. But there are several problems with autograding. The first is that autograders can't distinguish between major and minor mistakes. Consider the task to implement quicksort in order to sort a list from least to greatest. A student that uses quicksort to sort a list from greatest to least will fail almost every test given by the autograder. But morally, the student deserves no more than a couple points off for not reading the assignment carefully. In addition to viewing mostly correct code with minor bugs as totally or near totally incorrect, autograders can only detect errors in output. So if a student uses a wrong or inefficient algorithm but ultimately gets the right output, an autograder can't distinguish that from a student that efficiently implements the appropriate algorithm. Finally, the only output that autograders can provide is of the form, this is the output that your program gave for this input, but it should have given this other output. Whereas humans can actually note good and bad decisions that students made during their implementation and give feedback based off of that. So although there's good work being done on making autograders better at providing useful feedback, we wanted to find a way to make it feasible for courses to still provide human feedback, even as more and more students join. The basic goal we had was to try to enable courses to give human feedback to multiple students at once, rather than one student at a time. We would take all of the student submissions for any given task and cluster them into buckets where all the programs are not only equivalent, but also use a shared algorithmic approach. This way, any comments or feedback on how the task was approached could be made by looking at just one or two programs in the bucket, but still be applicable and helpful for all the students in that bucket. There are a couple of obstacles for this goal. Right off the bat, clustering programs into equivalence buckets is undecidable, but this isn't quite what we're trying to do. If two programs are sufficiently different, even if they are ultimately equivalent from an input-output perspective, we don't actually want to put them into the same bucket. Otherwise, we would be doing things like clustering implementations of quicksort and merge sort together, and it would no longer be the case that the same feedback could be given to all students in a bucket. On the other hand, if we do put two programs into the same bucket, we want to be certain that they are equivalent. Otherwise, we would run the risk of causing courses to give improper feedback to a subset of their students. So this calls for an extremely conservative approach to program equivalence. We only want to deem programs as equivalent when they are structured similarly and when we can prove that the programs are equivalent. We start with two expressions, E1 and E2, where we want to know if E1 and E2 belong in the same bucket. For clustering all programs into buckets, it suffices to know whether just two expressions should be put into the same bucket, because we can then just run lots of pairwise comparisons between the student submissions. We first break down the two expressions into sub-expressions, using a variety of inference rules that depend on the structure of E1 and E2. If E1 and E2 have sufficiently different structures, for instance, if one calls a recursive helper function while the other does not, then these inference rules will get stuck, and it will be determined that E1 and E2 don't belong in the same bucket. This honors the fact that if E1 and E2 are sufficiently different, we don't actually want them in the same bucket, even if they might technically be equivalent as far as input and output are concerned. As we break down E1 and E2 by invoking various inference rules, we generate an intermediate representation that consists of approximate subexpressions of E1 and E2, as well as a formula sigma prime. The idea is that as the evaluation progresses, E1 prime and E2 prime will get smaller and smaller, while sigma prime will get bigger and bigger, until eventually, we are left with just a formula sigma. Sigma is simply a logical formula, whose validity can be checked with an SMT solver like Z3. This final formula sigma will assert that E1 and E2 are equivalent. If sigma is valid, then it will mean that E1 and E2 are indeed equivalent, and so we can place them into the same bucket. But if the evaluation failed to reach a final formula sigma, or if sigma turned out to not be valid, then E1 and E2 won't be placed into the same bucket. The judgment that we use for our inference rules is this. We have gamma, a typing context for all of the variables that appear in E1 and E2, E1 and E2, which are the expressions or sub-expressions being compared, tau, the type of E1 and E2, gamma prime, the typing context for all of the variables that appear in sigma but not in E1 or E2, and finally sigma itself, the formula being generated by this evaluation. With this judgment established, I can state our paper's soundness result. If this judgment is derived using our system's inference rules, then the validity of sigma necessarily implies that E1 and E2 are equivalent. In other words, if we use the output of an SMT solver given sigma to determine whether E1 and E2 should be placed into the same bucket, then we will never place non-equivalent expressions into the same bucket. This is the main result of our paper. It's the result that guarantees that adopting our approach to facilitate human feedback in large courses won't cause students to receive feedback or grades that don't apply to them. Now that I've given a high-level outline of our approach, I'd like to walk through a concrete example of how our approach is used to identify equivalence. Here, we have two implementations of optEqual. They both return true when opt1 and opt2 are either none options or some options containing the same value, and they both return false otherwise. When we examine these two implementations manually, we can see that they're equivalent simply by considering each of the cases. In the first case, when opt1 is none and opt2 is none, both implementations return true. When just one of opt1 and opt2 are none and the other is some of something, both of them return false. And finally, when opt1 is sum of x and opt2 is sum of y, both implementations return x equals y. Since both implementations return the same output in all of the possible cases for the input, we can observe that these two implementations are equivalent to each other. In order to reason about the optEqual implementations, our approach will actually use these two inference rules. But right now, there's so much syntax on screen that it's impossible to see what these rules are actually doing. Both of these rules are for comparing a case expression to some arbitrary expression e prime. Since both implementations of optEqual used case expressions, we need to use both of these rules to break down the two implementations. Most of the details of the premises aren't super important. E term just means that E, the expression being cased on, is simple enough to encode in an SMT formula. We see that this is necessary because E actually appears in the formulas generated by these rules. If this premise weren't satisfied, then in order to break down the two optEqual implementations, we would have to use different rules from our system. The parts of the premise that concern freshening can also be ignored right now. The reason these premises need to be around to clutter up the rule is that a lot of care needs to be taken when we're generating our logical formulas. In ordinary programs, there's no issue with replacing the value of a variable by shadowing, and of course, there are no constraints whatsoever on whether variables from one program can have the same name as entirely unrelated variables from another. But in a logical formula, there's no notion of scope, no notion of shadowing, so if the same variable appears twice in a logical formula, then the two variables necessarily refer to the same value. A lot of the technical details in our system are for making sure that distinct variables never wind up with the same name, while on the other hand, variables that necessarily do refer to the same value in both programs are given the same name. But these details aren't essential to understanding how these rules actually work in practice. The main thing to know is that for each branch of the case statement, sigma I is a formula that asserts that E prime and the case branch's associated expression are equivalent. With this, we can understand the formula generated by these two rules. When case E of P1.E1, P2.E2, etc. is evaluated, it evaluates to E1 if E pattern matches with P1, E2 if E pattern matches with P2 but not P1, and so on. The formula that asserts that the case statement and E prime are equivalent states that if E pattern matches with a certain pattern Pi, and E doesn't pattern match with any prior patterns, then in order for the case statement and E prime to be equivalent, EI and E prime must be equivalent, which is expressed by sigma I. Returning to the optEqual implementations, we can begin to imagine how our inference rules might be used to unravel the two programs. What we would want to ultimately happen is produce a formula that reasons through each of the case branches and concludes that no matter what, the two programs produce equivalent output. So we should see that if both opt1 and opt2 are none, both programs return true. If opt1 is none and opt2 is some of something, then both programs return false, and so on. Here we have the formula that we get when we use our inference rules on the two optEqual implementations. We see that the formula really is divided into cases where opt1 and opt2 are both none, opt1 is none and opt2 is some of something, and so on. In the case where opt1 and opt2 are both none, we go through the first implementation's logic of checking whether opt1 is none and then whether opt2 is none. Since both of these hold, we assert that the output given by the first implementation is the same as the output given by the second implementation. Since both of these outputs are simply the Boolean true, we get the formula that true is equivalent to true. The other parts of this first case wind up being vacuously true, on account of the fact that opt1 and opt2 cannot both be none and some of something at the same time. For instance, this line is vacuously true because the hypothesis asserts that opt2 isn't none, even though we're in the case where both opt1 and opt2 are none. Similarly, this implication that spans the rest of the case is also vacuously true, because its hypothesis asserts that opt1 isn't none. The next case, in which opt1 is none and opt2 is sum of y, as well as the last two remaining cases, which I don't show, function similarly. Since the overall formula produced here is valid, our approach is able to show that the two optEqual implementations were equivalent. So we've gotten a glimpse of how our approach works in practice, and we know that clustering programs using this approach will never cause non-equivalent programs to receive the same feedback. But an obvious question that remains to be asked is whether clustering programs with this approach would actually be useful. Can clustering student submissions using this approach actually reduce the number of programs that need to be hand-graded enough to make human grading more feasible? And are the programs actually clustered in such a way that it's possible to give useful feedback to an entire bucket at once? To answer these questions, we implemented a tool for clustering standard ML programs and tested our tool's ability to cluster hundreds of real homework submissions from an introductory functional programming course. Here are the results of using our tool to cluster 12 different homework tasks. For every task except SAT, our approach was able to reduce the number of programs that needed to be hand-graded by at least 75%. And for all of the tasks, including SAT, at least 30% of the buckets produced are accounted for by just 10% of submissions that contained irregular errors or unusual approaches. There's certainly room for improvement, but I also want to note that the frequency with which any given submission is not needed to be individually graded increases along with the total number of submissions. This is because as more and more distinct buckets are created, the more likely it is that any subsequent program can be placed into one of the pre-existing buckets. This both means that our approach is likely to scale well, and that if the same assignment is given in a course multiple years in a row, buckets and their associated feedback from previous years can be leveraged to automatically give feedback to new submissions. Since our tool is able to significantly reduce the number of programs that need to be graded in any given year, and our tool makes it possible to utilize feedback from prior iterations of a course, I think our tool can make it genuinely feasible for courses to continue to provide human feedback, even as class sizes increase. The other question I want to address is whether useful feedback can be given at the bucket level. I have here the correctness statistics for each of the tasks we collected data from. There's an obvious outlier. For every task except TreeReduce, less than 15% of the student submissions were incorrect. But for TreeReduce itself, over 40% of submissions were wrong. There were over 3 times as many wrong submissions for TreeReduce than there were for any other task. So what happened? Why was this one task so difficult? When we looked at the buckets produced by clustering the TreeReduce submissions, we found that there weren't an exceptionally large number of students doing unusual things in their implementations because they were confused or just didn't know what else to do. Instead, we found several very large buckets of wrong submissions. To understand what occurred in these buckets, I need to briefly explain the objective of the TreeReduce task. Students were asked to write a function that, given a tree and a binary operator, produced the output of applying that binary operator in between each element of the in-order traversal of the tree. In order to do this in O of n work and O of log n span, students were told to assume that the operator passed into the function is necessarily associative. The issue that arose in the large buckets of incorrect submissions was that a significant number of students assumed that the operator passed into TreeReduce was necessarily associative and commutative. So no care was taken to ensure that arguments were passed to the binary operator in the proper order. This is a particularly tricky bug to catch because the most obvious binary operators one might use for int trees are neither associative nor commutative, like subtraction and division, or both associative and commutative, like addition and multiplication. So students that only tested their code on int trees were significantly more likely to make this mistake. But students that tested their code more thoroughly, for instance, testing TreeReduce when given a string concatenation function and a string tree, didn't make this mistake. When there are many students that exhibit a shared misunderstanding, our tool makes it possible to clarify this misunderstanding for all students that need it at once, rather than have to sift through every submission individually to find students in need of that feedback. So here are the main takeaways. Because of our soundness result, our approach can be used with the assurance that it won't cause students to receive improper feedback. The approach can significantly reduce the number of programs a course staff must grade manually, and once human feedback has been given, it can remain useful in subsequent years as long as the same homework assignment is used. And as we saw in the TreeReduce example, genuinely useful feedback can be given at the bucket level. I'd love to see this work adopted and innovated upon by functional programming courses so that growing class sizes don't prevent students from receiving the best feedback possible. I'd like to thank my co-authors Vijay Ramamurthy, Ruben Martins, and Umut Acar for their contribution in this project. And I'd in particular like to thank Vijay Ramamurthy, whose senior thesis was a valuable resource for preparing this talk. Thank you for your time. I'd be happy to take any questions now.